the Indonesia Mathematical Society IndoMS and the Institute for Research, Community Service and Business Development ITSB. Before we begin, let us take a moment to pray together.
Kita hidup
According to
di
each of
hari-hari
our
ini.
beliefs,
Saudara
we
sekalian,
ask for
kita
blessing
sebagai orang
and
Kristen
success
harus
for
tahu
today's
dan percaya
event. Please
bahwa
join me
Yesus
for a
Tuhan kita
moment of
yang
silence.
datang menjelma dari manusia berinkarnasi.
Thank you, ladies and gentlemen. Allow me to give a brief rundown of how this event will proceed. We will begin with welcome remarks, followed by two presentations from our esteemed speakers, a questions and answers sessions, certificate presentation, and finally the closing. Ladies and gentlemen, we will begin the event by listening to the Indonesia National Anthem Indonesia Raya. Dr. Samsu, please.
Mohon izin share screen. Share. Screen one-nya. Share sound and optimize. Thank you, Mrs. Lia. Mrs. Lia, your face is still mute.
Okay. I'm sorry. Now, let us proceed with the first about the welcome remarks. Ladies and gentlemen, we are honored to have Dr. Yunita Anwar, representing the Indonesian Algebra Society. She will deliver the opening remarks and share her insights on the importance of international engagement in advancing mathematical sciences. Please welcome Dr. Yunita.
Thank you, Ms. Lia. Bismillah. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Good morning, distinguished speakers, esteemed college students, and all participants who have a great interest in algebra. On behalf of the organizing committee, it is my honor to welcome all of you to the international webinar of algebra organized by the Indonesian Algebra Society. The host is Western region with the support of Indonesian Mathematical Society and the Center of Learning Development Institute Teknologi Sains Bandung. This event is designed to provide a platform for sharing knowledge, exchanging ideas, strengthening academic collaboration in the field of algebra. So we hope that today's presentation and discussions will inspire new perspective and open opportunities for collaborative research and contribute to the development of mathematical understanding both locally and globally. And to our invited speakers, Professor Evanian from Ferdowsi University and Dr. Puguh Prasetyo from Universitas Ahmad Dahlan, we sincerely thank you for your presence and your willingness to share your expertise with us. So we hope your contributions are truly valuable and greatly appreciated. And I would also like to express my appreciation to the organizing team for their dedication and hard work in preparing this international academic event. To all participants, thank you for taking the time to join us today. Once again, thank you very much.
Thank you very much, Dr. Yunita, for your inspiring message and continued support for academic collaboration. Next, we will hear from Dr. Dani Lukman Hakim, representing the Institute for Research, Community Service, and Business Development ITSB. He will share his thoughts on the institutional commitment to support global academic collaboration. Please welcome Dr. Dani.
Yeah, thank you for the opportunity. Good morning, distinguished speakers, respected participants, committees, and dear colleagues from overseas, from Ireland. On behalf of Institute for Research, Community Service, and Business Development of Institut Teknologi Sains Bandung, or Bandung Institute of Science and Technology. So I'm truly honored to welcome you to this international webinar of algebra. So this is actually a valuable event as one of our webinar series program that created in our institution. So I think this is one of our shared commitment to strengthen academic collaborations in the field of mathematics. To be honest, that actually I'm not a lecturer or scientist in this field, but in my opinion that algebra is one of the foundation to provide the logical in many innovation in computation, engineering, and also data science in our perspective. So therefore, I would like to express my deepest appreciation to all of the speakers, to the committees. Dr. Puguh Wahyu Prasetyo from Ahmad Dahlan University, and also Professor Ahmad Evanian from Ferdowsi University from Iran, for your willingness to share their valuable insight and expertise. Okay, I hope that today discussion will be inspire new perspective for all of the participants and research collaboration in the future, and also lasting for academic partnership among of our institution. Thank you, and I wish you all participants an engaging and fruitful webinar today. Thank you again. Enjoy your
Thank
webinar.
you very much, Dr. Dani, for your kind words and strong encouragement for research and academic synergy. Before we proceed to the main session, let's take a group photo together. We kindly invite all participants to turn on your cameras and give your best smiles. The organizing team will take the screenshot for documentation. Please turn on your cameras.
And we hope all the participants can use the virtual background share in chat room. Maybe we can wait for 1 or 2 minutes. Bu Lia, bisa dibantu ini snip atau screenshot atau dari saya aja?
Pak Samsul boleh.
Oke, di saya ada 2 tampilan ya, ada 2 layar. Oke, I will guide in bahasa ya. Rekan-rekan mohon on cam untuk layar pertama. Give the best smile. 1, 2, 3, smile. Okay, wait. And for the second tampilan kedua, mohon berikan senyuman terbaik. 1, 2, 3, smile.
Sehingga menghalangi.
Sudah Bu Lia, waktu tempat dipersilakan.
Berapa banyak yang daftar bukan hal yang paling penting. Yang paling penting yang daftar itu mewakili siapa.
Thank you, Mr.
Motivasinya.
Samsul. Thank you. Now we are ready to move the main part of today's program, the presentation sessions. Dr. Samsul?
Yeah. Thank you, Mrs. Lia. I will guide here for the main ideas in this webinar ya. Good morning, distinguished professor, college, Dr. Pugu, Professor Evanian, and all the participants. Assalamualaikum warahmatullahi wabarakatuh. Now let me briefly introduce our two distinguished speakers for today's webinar. Our first speaker, Dr. Pugu Prasetyo, maybe I will share the new curriculum vitae. Okay, this is okay, but I will share sort of two page ya. Dr. Pugu Wahyu Prasetyo, an associate professor of mathematics at Universitas Ahmad Dahlan, Yogyakarta, Indonesia. Dr. Pugu completed his bachelor's degree in mathematics at Yogyakarta State University, and both his master's and doctoral degrees in mathematics also at Universitas Gadjah Mada. He also conducted research visits as an international visiting graduate student at the University of Toronto, Canada, and later as a visiting professor there in about 2023. Dr. Pugu academic mentors include Professor Indah Emilia Wijayanti, from Universitas Gadjah Mada, and then Professor Helena Franz Jackson from Nelson Mandela University, and also Professor Ju Repka from University of Toronto. His research focuses on algebraic structures, graph theory, and mathematical education, and he has received multiple international grants and recognitions, including the SIF ya, Travel Grant to ICM 2022, and the AMS Simons Foundation Travel Grant to ICM 2026. In about 2024, he was awarded first rank academic leader in the Yogyakarta region. Now we are proud to welcome him to share his expertise and experience with us. Ya, dipersilakan, Dr. Bugu, time is yours.
Thank you, Dr. Tansul Arifin. Can you hear my voice? I'm sorry.
Yes.
Okay, yeah. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam.
Good morning, everyone. Distinguished
Stop share.
professor, colleagues, and fellow leaders. It is honor for me to deliver my research activities entitled Introduction to Partner Problems. And in this chance, I would like to thank to Dr. Junita as the representative of Indonesian Mathematical Society and Indonesian Algebra Society. And also, I would like to thanks to Dr. Dani as the Director of Research and Community Service and Business of ITSB. This agenda is a collaborative activities between ITSB, Indonesian Mathematical Society, and Indonesian Algebra Society. And also, I would like to start to share my slide. Sorry, Pak Ipin. Okay.
Yes.
Yep.
Jelas.
Yeah.
Yes. Thank you.
First, I would like to extend my warmest greetings to Professor Ahmad Irfanian. It is a pleasure to reconnect him after our memorable meeting at Universitas Gadjah Mada in 2018. I met him with my students attending the Professor Ahmad Irfanian talk 7 years ago. Okay, today I would like to start my talk with the history of radical theory, especially as the fundamental aspect in ring theory. So in 1808, Professor Wedderburn identified the difficulty of describing the structure of ring via linear transformation, and after that, in 1930, Code used this idea to study the nilpotency and the nil and nil ideals. And we can see this paper entitled on hypercomplex number presented by Professor Wedderburn is the fundamental paper for the development of radical theory, especially in the ring non-commutative ring theory. I also thanks to the committee for the invitation to participate in this collaborative activity. Okay, I will start with some fundamental concept from radical theory. We denote NR to explain the largest nil ideals of any ring R. And Amit Sur and Kuros introduced the notion of radical theory and also introduced the two radical class construction The first one is the lower radical class construction, and the second one is the upper radical class construction. So we will start with the formal definition proposed by Admitsur and Puros. If we have gamma is a class of rings, then the class gamma is called a radical class if satisfy these three following conditions. The first one is gamma is homomorphically closed, and the second one, the class of rings gamma also contains the largest ideals of A which belong to gamma. And the last one, the gamma of the ring quotient, the gamma of quotient ring A over gamma A is equal to 0. And furthermore, the ideal gamma A is called the gamma radical of A, and a ring A is a gamma ring if the gamma A is equal to A itself. And we have some equivalence condition with the previous definition of radical class. We also sometimes use this equivalence condition. For the example, we have this necessary and sufficient condition for any class of rings to be a radical class. So a class of rings gamma is radical class if and only if the first one, gamma is homomorphically closed, and we have the following condition. Gamma has the inductive properties, and gamma is also closed under extension. And the following condition explained in this on this slide, number 2 and 3, we have the same equivalent. This condition are equivalent to say that the gamma is a radical class. So to make us better understanding on the definition of radical class, we provide some example. And the first one, this is the first example of radical class and it was proposed by Cote in 1930. This class is the class of ring A such that for every A in A, there exists n larger and equal to 1, such that A power n is equal to 0, which is precisely in the class of all nil rings. And based on the investigation, this class of rings satisfies the conditions that makes the class to be a radical class. So this is the first example of radical class. The next one, and this radical class is one of the famous radical class. We also consider it as the Jacobson radical class. We start with the definition of the operation. So let A be a ring, and we define a binary operation. We denote with circle on A, and the operation circle is defined by these followings. A circle B is equal to A plus B minus AB for every A, B, and A. This operation is associative, and also we can infer that A with the binary operation circle is a group. So we can construct the class J consists of all rings A such that A with the circle operation forms a group. Clearly, the class of rings J is homomorphically closed and has inductive property, and then the class J is also closed under extensor. After being evaluated that this class satisfies three following conditions, so we can infer that this class is also a radical class, and this class is called the Jacobson radical class. Since the construction of radical class, the Jacobson radical class is also precisely the class of all quasi-regular rings. The next example, we provide a class of ring which is not a radical class. We have the class of all nilpotent rings, and this class is not a radical class since this class has not inductive property, has no inductive property. By the following counter example, we can construct with this kind of rings. So we already have two class of ring which are radical classes, and one example which is not a radical class. The first one, we have the nil rings, the class of all nil rings. The second one is the Jacobson radical class, and the third one is the class of all nilpotent rings, which is not a radical class. So the next concept that we have to master to continue this material, we have to identify or consider the special class. What is the definition of special class in the perspective of radical class? We explain two kinds of class of rings. The first one is a special class, and the second one is a weakly special class. Let mu be a class of rings, and the class mu is called a special class, respectively a weakly special class if mu satisfies these three conditions. The first one, mu is hereditary. So if we take any rings in mu, we have that all of ideals of A will be the member of mu. And the mu consists of prime rings, respectively consists of semi-prime rings. And mu is essentially closed. It means that if we have any rings A and any non-zero ideal I of A, which is the non-zero ideal I is an essential ideal, such that essential ideal is the member of mu. This condition makes that the rings to be the member of mu. So we provide the example of special class of rings. The first one, the class of all simple ring with unity is a special class of rings. For the detail of the proof, we can see on the slide. So we start with the hereditariness of this class, and then we can infer that if we take any rings in this class, that kind of rings will be a prime ring. And also, if we take any essential ideals of any rings A, such that the essential ideals is a simple ring with unity, so the ring A is the member also of this kind of class. So based on the explanation, we can infer that the the class of all simple rings with unity is a special class of rings. Okay, we will try to explain the next example. The class of all prime rings, and we denote it with pi, is also a special class, since we already know that any ideal of a prime ring is also a prime ring. So we can infer that the class of all prime rings is hereditary. And the second one, the class of all prime rings is actually consists of prime rings, and we know that the class of all prime rings is also closed under essential extension. As well, for the class of all semi-prime rings, we have the bigger class, since every prime ring is a semi-prime rings. So the class of all semi-prime ring should contain the class of all prime rings. And in this chance, we can infer that the class of all prime rings is a special class, and the class of all semi-prime rings is a weakly special class. Based on the properties that I stated before, since every prime rings is a semi-prime rings, so we can infer that every special class is also a weakly special class. The next concept that we have to learn to continue our study on the Gardner problem, we have to identify the relation between the hereditary and the regularity and the close under subdirect sum of class of rings. So we provide the definition of hereditary here, and then we provide also the definition of regularity of any class of rings here. And also we provide the definition of a class that is closed under subdirect sum here. Based on the definition, we can infer directly that every hereditary radical class is also a regular class. And furthermore, since previously we have known that the class of all prime ring is hereditary, so we can infer that the class of all prime ring pi is also a regular class. As mentioned before, we have two radical class construction. The first one is lower radical class, but in this chance, we have to focus on the upper radical class constructions. Since we start with the class of the special class, so let Faro be a class of rings, which is a regular class, and we have to seek the largest radical class gamma, such that the intersection between the Faro is equal to 0. This radical class is called the upper radical class of Faro, and it will be denoted by U Faro. And the contraction of the upper radical class U Faro of regular class of Faro will be explained in the followings. We have this one. This is the construction of the upper radical class. So what is the mu Faro? The mu Faro is all of ring A such that A has no non-zero homomorphic image in Faro. And we can infer that if we have a regular class Faro as a regular class, and then we can construct this following class of rings, so we can investigate and we can check this class of ring is a radical class. And also the intersection between this radical class with Faro is equal to 0. And we have the mu Faro is the largest radical class having 0 intersection with Faro. And the next concept that we have to study is a special radical. So what is the special radical? A special radical is the upper radical of the class of all the upper radical of a special radical. So the definition of special radical is the radical class that is constructed by a special class. Since previously we know that the class of all prime rings pi is a special class, so the upper radical class of pi is also a special radical class. And this kind of radical is called prime radical, since it is generated by the class of all prime rings. So we consider it as a prime radical, and it is denoted by beta, since the mathematician who worked on this topic is Professor Bayer. So mathematicians consider it as beta. Explain that this is precisely the prime radical. Furthermore, Snyder saw all special radical from a complete lattice with the prime radical. Beta is the least element of that lattice. And in 1985, Professor Halina Korolsuk, this is the previous name of my former promoter, Professor Halina Franciszek, introduced star ring. What is star ring? Star ring is a ring which is a prime but has no non-zero homomorphic image in pi. And Professor Halina Franciszek in her research state that the upper radical U pi track pi A is an atom of the lattice of special radical. What is atom? Atom is the smallest element of that lattice, but bigger of the least element. So the atom is the covering of the least element. I explain again. The atom is the element of that lattice that covering the least element. But the class of all star ring is not a special class. We can find some counter example in the paper of Professor Halina Franciszek. And because of this condition, she developed the essential closure of the class of all primary star rings, and this essential closure is denoted by star K, and this class is a special class. So the upper radical class of star K, which is denoted by U star K, is a special radical. So we can take some relationship between known radical class today. This is the part of the lattice of special radical class. We have this one as the prime radical, beta, and then this is the Levisi radical, and here is the Jacobson radical. And all radical shown in this on this slide are special radical. But the natural question we can ask, where is the position of mu star K as a special radical? So this is the main problem of this talk. So in 1988, Professor Barry Gardner, my former supervisor, Professor Halina Franciszek, he asked whether the prime radical beta coincide to the mu star K. And this condition is equivalent with another problem. For example, Professor Halina Franciszek explained that this problem is equivalent with the question whether every atom can be represented as this one. The positive answer of this following question is also related to the extra special radical, which is explained in this paper. Furthermore, Professor Gronewald from Nelson Mandela University is also Professor Leavitt defined a beta class, which is a class offering mu such that the upper radical of mu is equal to beta. This condition makes the question equivalent to ask if the star K is a beta class. So the Gardner problem is related to some fundamental question in radical theory. Furthermore, Rowan defined a prime essential ring, and later some research outcome from Professor Helena Franz-Jackson also used a prime essential ring as a tool to answer the Gardner problem. Furthermore, Professor Helena Franz-Jackson already gave a partial result of this question in the perspective of the lattice n radical. So if we study more on radical theory, we have some further properties of radical, which is not only special radical, it is also super nilpotent radical, for example, and then n radical, normal radical, and so on. And in this paper, the reference number 12, which is Professor Helena Franz-Jackson research outcome, explained that the Gardner problem has a positive answer if complemented in the lattice of all n radical. In another perspective, Professor Helena Franz-Jackson also suggests to solve this following problem in the perspective of spatial atoms. And in the reference number 13, we try to bring the concept of starring to star P modules, and we would like to solve the Gardner problem in the module theory perspective. And this is the part of my previous dissertation in 2018. We also used prime essential ring to construct some radical class, and we use this to try to solve the Gardner problem. However, in general, if we have an arbitrary ring R, it is still unknown whether the U star K R is the intersection of all prime ideals of R, or only a subset of them, since this following condition remains open up until now. So it is good to continue to study for the solution of the Gardner problem. And Professor Helena Franz-Jackson collaborative paper with Professor Dr. Indah Emilia Wijayanti and also Professor Sri Wahyuni in 2015 published a beautiful paper, and they call the radical class mu star K as the Indah radical. It means that Indah is Indah plus Helena. So we start from this notion, we call the U star K as Indah radical. So we previously I mentioned about the n radical, so I will explain the detailed definition of n radical. So what is the n radical? N radical is a radical class which is left strong, left hereditary, and contains the prime radical. And we also consider the following construction from, and it is constructed by Professor Helena Franz-Jackson in her paper. This construction is developed to solve the Gardner problem. And finally, he proposed this one as the necessary and sufficient condition for U star K to coincide the prime radical. And we have these two following necessary and sufficient condition. in the perspective of lattice of all n radicals. And furthermore, we also try to solve the Gardner problem in the another perspective. For a radical class alpha, we have S alpha denotes the class of all alpha semi-simple rings. And this is exactly the class of all ring R, such that R has no non-zero ideal in the radical class alpha. And then also we consider the epsilon as the class of all prime essential ring. That is, the semi-prime rings are whose every non-zero prime ideal is an essential ideal. And we have from the previous research that minimal element of the lattice of S of all spatial radical are called spatial atoms. So in my latest published paper in this year, published by ASEAN European Journal of Mathematics, which is my collaborative research with Professor Indah Emily Wijayanti, Professor Halina Franz-Jackson, also Professor Zorebka. We propose this necessary and sufficient condition. So the Gardner problem has positive answer, which is equivalent to say that mu star k is equal to beta, or we can say that u star k coincide with the prime radical if the following condition equivalent, this following condition equivalent with these conditions. The proof of this necessary and sufficient condition can be seen in this the reference number 14. But in this chance, we skip the proof since it is quite long, so we can try to see directly on the paper. So based on investigation, we actually have some necessary and sufficient condition, but we know that the Gardner problem remains open. So research on the radical class, especially for the Gardner problem, should be continued to investigate the fact about the positive answer on the Gardner problems. But beside we try to seek the truth about the Gardner problem, we also mathematician also algebraists also comparing the properties between the prime radical beta and the mu and the u star k or indah radical. So the algebraists also try to compare the properties between prime radical and indah radical. And we know up to 2017, we have the following condition. The prime radical beta is left hereditary, right hereditary, left strong, and also n radical. And we have the following condition also. Professor Alina Franz-Jackson proved that the indah radical also satisfies these criteria. We can check the truth about this table on the paper number 2 and number 12. And recently, Professor Gardner with his colleagues, Professor Kojuhari, in their paper and in this presentation, we use the reference number 15, 16, and 17. They give a new concept of corner hereditary, corner strict, and very corner hereditary, and hereditary for phantom corner or HPC. And we explain the detailed definition on the next slide. This is the definition of corner hereditary, and we also provide the example of this class. And this is the definition of corner streak, and also we provide the example of this class. And this is the definition of the very corner hereditary, and we consider some example proposed by Professor Gardner and his colleagues, Professor Kojuhari. And the last one, the hereditary for phantom corner. The definition of hereditary for phantom corner is here, and also we can check some further example of hereditary phantom for phantom corner of radical class were also explained in the reference number 16 and 17. Based on these properties, it is a natural question rise whether the indah radical satisfies this four condition, satisfies or not. This is a natural question since the prime radical beta is also corner hereditary, the prime radical beta is also corner strict, and the prime radical beta is also very corner hereditary. And in Professor Gardner's papers, Professor Gardner also proved that the prime radical beta also hereditary for phantom corner. So the natural question whether the indah radical satisfies these following criteria. And based on our investigation, that indah radical also satisfies these following criteria, but perhaps I will try to explain later, since this result has been considered to be hopefully to be published at Barcang. Okay, I think and that's all for today. Before I close, I would like to express my gratitude to my doctoral supervisor, Professor Indah Amelia Wijayanti from Universitas Gadjah Mada, and also my former co-supervisor, Professor Halina French Jackson, who helped me to understand about radical theory, and also she also explained about the philosophy of radical theory, since in the perspective radical theory, we separate the good things and the bad things between inside the rings. So this is the philosophy that we can try to implement in our daily life, since we have to separate between the bad things and the good things. And also, I would like to express my gratitude to Professor Joe Repka. He previously worked on the code conjecture, and I also work on the same topic. So we did a collaborative research from 2016 in my first visiting at University of Toronto, and also I continue my collaborative research with him until now. But currently, Professor Joremka is being hospitalized. So I would like to ask all of you to take a pray for him. Hopefully, Professor Joremka will be recover soon. Finally, thank you very much for your attention and for being part of this discussion. And in this chance, I would like to propose to say that algebra unites us. Thank you so much. Assalamualaikum warahmatullahi wabarakatuh. The time is for Dr. Samsul Arifin again.
Ya, Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Dr. Pugu. I think the Q&A session will provide after the second speaker, and Now we can move to the our second speaker. But before that, I will start share screen about his new curriculum vitae and some information ya. Share screen 2. Okay. Our second speaker is Professor Ahmad Evanian, a full professor at Firdausi University of Mashhad, Iran. He obtained his BSc in pure mathematics from Firdausi University in about 1988, and then Master of Science in Algebra from Tehran University in about 1990, and his PhD in pure mathematics also, especially group theory from Cardiff University, United Kingdom, in about 1995. Professor Arvanian has served in numerous academics and administrative roles, and including Dean of the Faculty of Mathematics Science, Financial Vice Dean, and currently as Head of Mathematical Science Planning at the Ministry of Science, Research and Technology of Iran, as well as Director of the Curriculum Planning Committee of the Iranian Mathematical Society. His main research interests include group theory, algebra graph theory, probability group theory, and combinatorics. Professor Evanian has supervised more than 80 postgraduate thesis, author over 60 international journal papers, and co-authored several books in both Persian and English language, including miscellaneous topics of group theory, published in Italy. He is also a long-standing member of the Iranian and American Mathematical Societies, and has chaired or served as a committee member for numerous international group theory conferences around the world, including the upcoming 8th Biennial International Group Theory Conference, which will be held at Universitas Gadjah Mada, Indonesia in this year. We are deeply honored to him here today. Professor Evanian, the time is yours. I will stop sharing.
Can you hear me?
Yes, Prof. Clearly.
Okay. So thank you very much for introducing me. So first of all, I would like to thank the ITSB, Indonesian Mathematical Society, and Indonesian Algebra Society. What I would like to mention very general, not in a specific the outline of my education, and particularly algebra education. As you know, sometimes it's difficult for us to define and explain about algebraic concepts. So sometimes we may combine these concepts to some other fields.
I'm sorry,
like
Prof.
Yes.
I think you not share the presentation, or maybe from us.
Let me check again.
Yes. still trying to sharing. Yeah.
Or not yet?
Yes.
Is that
Clearly.
clear?
Yes.
All right. So, as I mentioned, I would like to give some suggestions to explain algebraic concepts by using two in mathematics, graph theory and probability. So let me just explain about the branches of mathematical sciences. Usually, as our department, we split mathematical sciences in three: pure mathematics, applied mathematics, and statistics. And each one consists of some subtopics, some branches. For example, in pure mathematics, we have algebra, geometry, topology, and so on. And also, we have numerical analysis, differential equation, dynamical system, operation research, control and optimization, graph theory, discrete math, and so on. And similarly, in statistics, we have some sub-branches like descriptive statistics, source compelling concepts, regression, data science. Would like to just explain take algebra from the pure mathematics, the first one. And from the second one, I would like to take graphs from discrete mathematics. And from the third one is the probability. So I would like to combine all together to explain some interesting way to explain algebraic concepts. Now, if you take algebra, we have many like groups, modules, rings. If we combine with group theory, and if we combine just groups, rings, any algebraic subject of algebraic graphs. And also, if we combine linear algebra, in linear algebra, we have matrices, we have and so on. With graph theory, this is that just, and also we may have coding theory by combining some topics in algebra with linear algebra, right? We can combine finite fields or polynomial rings with vector space and matrices. In coding theory, we have linear code, we have cyclic code, and so on. Now, I'm going to start with the definition of probability. What's the definition of probability? Is the probability of an event is the number of ways which can be happen to the total number of the ways, total number of outcomes. If A is an event, the probability of A, number of ways A can be happen to total number of outcomes, right? For example, if you take a dice, so put A to have number one and B an event having numbers 2 or 5, and C as an odd number. So probability to have event A is 1/6 because we have only one case. And also the total number of cases is 6. So the probability of event A is 1/6. And similarly, of having an event B is 2/, because we have two cases, 2 and 5, and the total number of cases is 6. And similarly, for the probability of an event C is 3/6, right? Now, let me move to some main just concepts in graph theory. First of all, you can see that when we talk about a graph, we have two main sets. Age sets, right? And we have a function. The function which can be explained that when we have an edge between any of two vertices. So we usually denote graph by G. Because we are going to explain something denoted by G, so we may denote a graph by gamma and group by G. And let me just let me remind you some important and some known graphs. When we talk about a path, we denote by Pn, so we have n vertices, and we have n-1 edges. And every V2 is adjacent to V3. So until Vn-1 is adjacent, and the number of edges is n-1. For cycles, cycle Cn, we have again n vertices, but here we have n edges because we have an edge from the vertex Vn to V1. So in a cycle, the number of edges and the number of vertices are the same. So we have n vertices and n edges. For complete graph Kn. So in complete graph, we have n vertices and we have an edge between any of two vertices. So all vertices are just have 3 vertices and 3 edges. For K4, we have 4 vertices, but here we have 6 edges because we have an edge from V1 to V3 and also V2 to V4. And K5, we have 5 times 4 is 20. By 2 is 10 edges. So in Kn, we have n vertices, and we have n times n-1. Now, for complete bipartite graph means that the vertex set consists as the disjoint union of two sets, A and B. So A, A1, A2, An, and in B, we have also M vertices in the second set, and there is no intersection. So KNM means that we have N vertices. Now, how about the edges? We don't have any edge in set A, and similarly in set B. So the only edges coming from a vertex from set A to a vertex in set B. The number of edges is n times m. For example, K2, 3, we have 2 vertices A2 and third vertex. So A1 is adjacent to all of B1, B2, B3, and also B2 and B3. So here we have edges because 2 times 3 is 6. In a special case, only a singleton has only one vertex as a singleton set. In this case, for example, K13 is a star graph, and in the second set we have 3 vertices. Now we can generate to complete R-Python graph. So in this case, we have R disjoint sets A1, A2, AR. The vertex set is this edge in any sets, but if we take from any sets to another have completed bipartite graph. For example, K2, 3, and 4, we have 2 vertices in A1, 3 vertices in A2, in A3. And you can see that from A1, the vertex from A1 is adjacent to all other vertices in A2 and A3. The number of vertices is the just summation size of all sets. So it's N1 plus N2 until plus NR. And also for the number of edges, we have this one. Also, if you take a vertex from a graph of all vertices, like Y, such that Y is adjacent to X, that the size of neighbors of X is called the degree of X. So the degree of X adjacent to X. For example, if you take this graph, so we have 6 vertices, you can see that the degree of V1 is 1 because V1 is adjacent to V2. There is only vertex V2 which is adjacent to V1. But for V2, the degree is 4 because V1, V3, and V4, they are all adjacent to V2. And similarly for the degree is 3, no vertex which adjacent to V0. So V6 is called an isolated vertex. And also, if we have a vertex, if we have an edge from a vertex X to itself, then it's and sometimes we may have between 2 vertices, so it's called multiple edges. The graph with no loop and no multiple are mostly assume that all graphs are simple. So algebra, we have group theory, linear algebra, ring theory. In group theory, we have some topics which are very important in group. Infinite group, we have presentation of group, representation Ring theory also we have commutations and many topics in ring, as Prof. Pugo mentioned about radical ring. So to start my main topics, combine graph with algebraic structure and also probability. So I start to define a concept which is abelian group through just the standard definition and also graph and probability. We are talking about a group. It means that we have a binary operation, right? We can denote by a star. So just all elements in non-empty operation, and we have associativity. Star B then times 2 C is A star times element, right? And also the inverse, add an extra condition, which is if you take any or commute, so if A star B is equal to B star A, then we can say abelian group or commutative group. For example, if you take S3, in S3, which is a symmetric group, on 3, if you take two elements, 1, 2, and 1, 3, they are not commute. So 1, 2, 1, 3 is 1, 3, 2, but 1, 3, 1, 2 is 1, 2, 3, and you know that they are not abelian. But if you take cyclic groups, that's a cyclic group of order 6, the elements is X is a generator of the group Z6, so we have 6 elements, identity, X, X squared, X cubed, and X to the 4. X to the 5, right? Also, we have dihedral group. Dihedral group is by 2 elements, right? By A has order 2, and we have a relation B is equal to A inverse. We have 8 elements in dihedral group in D8. Group D8 is not abelian, because if you take, you can see that AB ABA is B, but A times AB is A squared B. Right. Now, from here, I'm going to use graph theory and probability for just defining and to deal with the abelian groups. So I would like to give some more things about abelian group through the graph and probability. A graph. Suppose that G is a, I am going to define a graph which is called commuting graph. So the commuting graph related to a group G is a graph. The vertex set consists of all of the group. And if you take two elements, x and y, we can say that x is adjacent to y if they are commute. So if xy is equal to yx, we will have an h between x and y. Now, look at the first example, S3. In S3, we have 6 elements, so we have 6 vertices. Identity commute with all other elements. So identity is adjacent to 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. Right of edges is 6. You can see that we don't have edge between 1, 2, and 1, 3. Because they are not commute. And similarly, there is no edge between 1, 2, and 1, 3. Let's two. For cycle, right? And here we have an edge between any of two vertices, because if you take, as I mentioned, Z6 is an abelian group, so all elements are commute, right? So not the commuting graph of Z6 is K6, is a complete graph. For dihedral group of order 8, right? So here this is the you see an A square commute. 8 is adjacent to A. Let me just here the
Dear all participants, I think the connection between Iran and Indonesia more complicated ya. In bahasa jarak Iran Indonesia itu sangat jauh ya. So maybe we can try to wait update from Professor Ervanian. Maybe two more between 2 and 5 minutes. Okay, we will wait him.
Can you hear me?
Oh yes, Prof. Welcome back.
Okay. Okay.
Maybe you can start the presentation again.
For the internet expert is webcam, maybe it's better. Now let me again share a screen. Can you see?
Yes, clear.
Can you see my slide? Okay. So I mentioned that just we can define an abelian group through the graph. So we can say that a group is abelian the commuting graph is a complete 6. is abelian because the commuting graph is a complete graph, is K6. Now, let me define the probability for the group as the commutativity degree. So suppose that G is a finite group, so the commutativity degree of a group G, we can denote so the number of pairs, right, divided by the total number of pairs, which is order of G squared. So this is the commutativity degree. If we compute the commutativity degree for S3, you can see that identity. So identity commute with us and also itself. So we have 6 cases, 6 pairs. The second one is for element 1, 2. So 1, 2 commute with identity and itself. So we have 2 cases. So the total number of commuting pairs is 18 divided by the total so the commutativity degree of S3 for the cyclic group. For Z6, the commutativity degree is 1 because all elements are commute. So the total number of commuting pairs is exactly the total number of all possible pairs. So we have 36 over 36 is 1. For dihedral group is 5 over 8. Now, we can define abelian group through this probability. So we can say that the group is abelian if and only if the commutativity degree is 1. So why this commutativity? So the important is that in 2 cases, abelian or non-abelian. But for non-abelian group, we can also give a value, this amount of the probability. So sometimes when we want to prove a we don't need to have all elements commute. They are enough to prove the theorem. So the commutativity degree will give a tool to improve or resolve group from abelian group to non-abelian group. Let me give some results. Here are some results about the commutativity degree and about the graph. So if G is a finite non-abelian commutativity degree is at most 5 over 8. The central factor is isomorphic to a non-cyclic group of order 4. And just give a formula, the commutativity degree in terms of the sum of the size of centralizers. You know, the centralizer of an G is the number of element commute with X. So the number of elements which are commute, that's the centralizer. And you can see that the center of a group consists of all elements which commute with every element in group G. Now, if you commuting graph, you can see that the size of the centralizer, or even we can see that the neighbors, the set of neighbors of X is the centralizer. So we can express centralizer by the neighbor of an element, the centralizer of an element X by the set of proof that the commuting graph is always connected. because if you take any two vertices, they are adjacent, or even we can have a path through these two elements by the identity. The shortest length of shortest cycle is 3. And also with the commutativity degree of direct product is degrees. We have a lower one for the cubic number, and we can also see that if we have two isomorphic group, then the graphs, the commuting graphs, and are isomorphic, and also the commutativity degree, they are equal, but the converse is not true. Right. Now let me just give some things which are important for our teaching of abelian groups by these concepts. The first activity which we may have in our classes to give homework and exercises through graph and probability. For example, we can ask our students to compute the commutativity degree for symmetric group S3, which I have already done, and S4, and also we can ask them to draw the graph, the commuting graph for the symmetric group S3 and S4, right? And then they should conclude that S3 and S4 are not abelian because by two ways, the commutativity degree of both of them are not 1, and their commuting graphs are not complete graphs. Now, we can also ask them to find the degree of any vertex in both graphs and compare it with the centralizer of X. So it will explain that the centralizer is the neighbors of every vertex X, right? And also, we can ask them for the conjugacy class of these two groups and compare the size of conjugacy classes of these two groups by the commutativity degree of S3 and S4. Now, this is some sort of questions we can combine abelian group. We can just explain deeply about abelian group through two tools, graph theory and probability. Also, we may ask our student for some computation through some softwares, for example, GAP and SAGE. So we can ask a student to write a program to find the just commutativity degree for the group of order 2 times n, for example, for n between 2 and 20, right? So it can be it can be done by software GAP or SAGE, or just commutativity degree, draw the graph for group S3, D4, Q8, quaternion group, Z8, and A4, right? And also, we may ask them to compute the commutativity degree for subgroup of each of groups, and for the just quotient group, right? And compare the commutativity, these three together, just the commutativity degree of the whole group, the commutativity degree of subgroup, and for the quotient group. Now, we give some small project. We don't need more background about this project. For example, we may ask them to give a relation between the commutativity degree of a group and the number of ages, right? So they can find a relation, a formula for the number of ages through the probability. It means that if we have a graph, then we can count the number of ages and then find the commutativity the number of ages. Now, to just understand deeply about abelian group and non-abelian group, we can define two new concepts. I just gave the name for abelian. So the group G is near abelian if the commutativity degree is bigger than or equal to half, and is far abelian if the commutativity degree is less than half, right? So for the following groups, we can ask students to determine for what values of n dihedral group, alternating group, and symmetric group are near abelian or far abelian. For example, for S3, we can see that the group is near abelian because the commutativity degree is 1/2. Also, we may have some proposal just according to this. For example, sim group, alternating group, and dihedral group for any positive integer n, right? Not for just some special cases. What's the general? And also some graph properties in counting graph of these groups, for example, for independence number or number. By using two tools, graph theory and probability. Now, let me move second concept. I'm going to define normal subgroups. So you know the definition of normal subgroup. So if G is a group, normal subgroups, if we have this property, if the left coset XH is, if we have this property, then we can say that H is the normal subgroup. You can see that the left cosine of X and H for S3. For S3, we have, if we consider two subgroups of order 2, identity and 1, 2, and subgroups of order 3, right? So identity 1, 2, 3, and 1, 3, 2. So you can see that here, H is not normal because, for example, 1, 3, the left coset 1, 3, H is not equal to H1, 3. But K is normal. Now, I'm going to associate a graph to normal subgroups. So the graph is that if we set A consists of all elements of the group X, and set B is the set of B. Now, if you take an element, I'm going to X in set A, and a subgroup H in B by this relation. So if the left coset xh is equal to the right coset hx, we will have an h between x and h. Now, here for symmetry group S, so we have 6 elements and we have 6 subgroups. Look at the graph. This is a bipartite graph. So in the first row, you have 6 elements, and the second row consists of 6 subgroups. Now, what's the definition of normal subgroup through this graph? The degree of H is the order of G, right? Then is normal. H1 is identity sub-elements. It means that the left coset and right coset of each of these 6 elements are equal to H1. And H5 is a subgroup of order 3. H5 normal and H6 are normal. So this is the definition of normal subgroup through these graphs. How about the probability? We can also define a probability for a subgroup to be a normal. So if we take a fixed subgroup H, so we define the probability of subgroup by thus PHG is the number of elements such that the right coset and right coset are equal. Divide by the number of elements, divide by the order of G. So here also we can see that if the probability is 1, again is equivalent to is a normal subgroups. So this is also just probability. So let me move a little bit because there is no more time. So the third concept is in the ring. So I'm going to define element in a ring. So if you take an element X in R, in ring R, is called a zero divisor if there exists a non-zero elements Y such that XY is 0. So you can see that 0 is always zero divisor, right? But we may have some more other elements, not only 0. For example, for Z12, the set of zero divisors of R, and if we have 0 element, we can denote by Z star of R. So you can do that for the Z12, the set of zero divisors are 2, 3, 4, 6, 8, 9, and 10. For example, 2 is zero divisor because 3 times 4 is 0. So this is the definition of zero divisor. Now, I'm going to define a graph, a zero divisor graph. So if you take all in a ring as a set of vertices, and a ring we can add to Y if the multiplication is 0, right? So for example, for Z6, you can see that we have 6 elements, right? Now 0 is adjacent to all other vertices because 0 times 1 is 0, 0 times 2 is 0. So we have an H between any of elements here. You can see that 1 is 0, but 2 is adjacent to 3 because 2 times 3 is 0, right? So this is the zero divisor graph. Now, how about the zero divisor through this graph? So we see that X is a zero divisor element in R if we have one of these two conditions. So if the degree of a vertex is at least 2, or x squared is 0, because if x squared is 0, it means that x times x is 0, x so if you take this graph, you can see that 2 is a zero divisor because the degree is 2, but 1 is not zero divisor because the degree is 1. 4 is zero divisor because the degree is 4. To 2. So this is another way to consider zero, and we can also, so important just result from this graph is that we can also graph. So if you take, you know that the integral can be such that AB is 0, so Z5 also in integral any non-zero vertex is 1 and x squared not equal to 0. And we also define a probability for an element x to be zero divised. This is the probability, and we can say that x is a zero divised if the probability is bigger than or equal to 2 over the size of L. Now let me move for more suggestion, right? So similar to these three concepts which I define and explain through a graph, associate graph and probability, now we can also define a graph and probability for these concepts in group theory and ring theory. So for group theory, we can take cyclic group, cyclic subgroup, center of group, centralizer, conjugacy classes, number of conjugacy classes, nilpotent group, soluble group, simple group, and so on. And also for ring, we can also define invertible elements, nilpotent elements, idempotent element, regular element, subring, ideal, prom ideal, maximal ideal, division ring, field, and so on. So this is just a suggestion to use group to use graph theory and probability in our teaching of algebra. So when we are teaching algebra, we may use some of these graphs to explain more and deeply and easier for students. So thank you very much, and sorry for taking your time.
Okay, Alhamdulillah. Thank you, Professor Ahmad Irfanian. And now, both of speakers have finished their talks, and now we will open the floor for a Q&A session. So please kindly note your questions as we proceed. And participants, all of you are welcome to type your questions in the chat box ya, or maybe you can raise your hand to ask directly. Maybe for in bahasa is ada quote ya, ketok tular. Maybe I will start the session, Q&A session, this session for one question to Dr. Pugu. Dr. Pugu, maybe this is one package, yeah. What is the main idea behind the Gardner problems in mathematics? And I amazed yeah with your caption yeah, or your phrase yeah. Algebra units us. In your opinion, in what way can the structure of algebraic theories, yeah, such as maybe radicals and maybe the other special classes, yeah, symbolize collaboration among mathematicians, yeah, across institutions and maybe countries. Thank you, Mr. Pugu.
Thank you, Dr. Samsul Arifin, for the question. So perhaps I would like to explain about the motivation of Gardner problem, since the Snyder explained the lattice of all spatial radical, and currently we do not know about the position of indah radical on that lattice. So the main problem is the closest position for indah radical is the prime radical. So the natural question whether the prime radical coincide with the indah radical. So this question is the natural question, since we do not know about the position of indah radical yet. And after being investigated by some prominent authors like Professor Franz Section, Professor Grunewald, and also Professor Gardner himself found that some properties hold for a prime radical. So it is nice to continue the investigation for whether the current property for prime radical also hold for indah radical. And actually the implementation of radical theory basically for the development of ring theory itself, but for another implementation we can see but we need another concept, especially for example like a Lie algebra. So in the topic of Lie algebra we also found some concept of radical of Lie, and can be implemented to identify the the switch DAA, and that if we have Lie algebra, and the Lie algebra can be decomposed to be a compact Lie algebra and its radical, so we can infer that kind of system to be stabilized, and this concept can be implemented in robotics with things from the recent result on the implementation of Lie algebra, but this concept is using the concept of radicals. And also, for example, I found some paper implement the Jacobson radical to I think like to generate like a code in the coding theory, but for more detail I cannot explain for today. Maybe for the next activity I will try to explain how the radical theory be translated in another field of algebra. I think some research paper wrote by Professor Ahmad Ervanian also related to Jacobson graphs, and I follow his paper, and it is so beautiful paper. Thank you.
Okay, thank you, Dr. Pugu. And I think some minutes ago, there one participant raise hand. His Muhammad Nabil, silakan. You can write it or try to ask directly. Dipersilakan, Nabil.
Baik, Pak. Tes, apakah suaranya sudah jelas terdengar?
Ya, terdengar.
Sebelumnya mohon maaf, saya nggak bisa on cam karena laptopnya sedang bermasalah di kamera. Jadi di sini saya
Punten, Nabil, you want to ask for Professor Ervanian or to Dr. Pugu?
saya ingin bertanya ke Profesor Ervanian.
Can you translate first to English? Kalau ke Dr. Pugu mungkin masih paham ya, but for Professor Ahmad Ervanian, you can translate first to English.
You may translate to English.
Aduh. Ya, sebentar ya. Kalau begitu ke Profesor Pugu aja deh.
Oke, dipersilakan. You can try maybe Google Translate write it first and ask directly the result translation.
So he may ask you in Indonesian language and you can translate to me.
Oh ya, Nabil, bisa juga Anda ini dulu tanyakan dulu in bahasa and we can translate for Profesor Ahmad.
Oh, begitu aja ya, Pak. Oke,
Ya.
langsung aja ya. Tadi dalam materi yang sudah disebutkan Profesor Ahmad Ervanian, itu kan ada beberapa aplikasi seperti commuting graph, zero divisor graph, dan lain-lain. Nah, itu kan hubungannya antara teori graf, probabilitas, dan aljabar. Nah, sebenarnya apakah ada aplikasi lain selain yang tadi itu di bidang aljabar yang sekiranya bisa dieksplorasi atau memiliki potensi yang besar untuk dieksplorasi lebih lanjut gitu, Pak, dengan menggunakan teori graf dan probabilitas tadi ya, seperti itu kira-kira pertanyaan dari saya.
Oke.
Bisa di ini, Pak.
Ada lagi? Satu aja? Atau satu dulu?
Udah, satu dulu.
Okay. Professor Ahmad, I will try to translate the question from our student. Maybe nanti kalau keliru di ini ya, di revisi ya, Pak Pugu. Kalau
baik, Pak.
Bahasa Inggris saya juga mungkin kurang oke. Khawatirnya ada yang keliru nih. Prof, as your presentation before, there are several application ya, such as the notion of zero divisor and the others, which are related to some topics, maybe in apa algebra itself, and you notion the apa probability and the others. Is there any connection, more connection ya, between this topic with the others topic, maybe science apa data science or computer science? Thank you.
Yes.
All right. So thank you very much for your question. As you know, at the beginning of my talk, I just separated mathematical sciences in three branches: pure mathematics, applied mathematics, and statistics. So algebra coming from pure mathematics, graph theory coming from applied mathematics, and statistics coming from the probability coming from the statistics. So this is just something as interdisciplinary between three topics: algebra, graph theory, and probability. So the first thing is that this connection would help us to translate some graph properties to algebra properties, and also some amount of the probability in graph theory or in algebra. So that the situation, the position of these topics is an interdisciplinary, but mainly we focus on some algebraic concepts. So in just the aim of this talk is to use graph theory, not very deep graph theory, just very elementary graph theory and elementary probability to explain more and attractive for students about algebraic concepts. Because sometimes in our teaching, when we are just writing a definition or a theorem, so a student that actually they don't like to have only in pure in definition as a pure concept. They would like to have some things which we can show these concepts through something on the blackboard. So we can use the graph and probability to compute, to deal with something which are interested for students. So graph theory, drawing a graph, computing something through the software is interesting for students. So we can use these two tools to give more attraction for students. Now, from the statistics, I just mentioned the probability, but the probability is only one of the main and easy concepts in statistics. We can just find something more in statistics and also in graph theory. So the motivation of these topics is to use one or two other topics to the main topics for our teachings. And the important things is that we can give some connections between algebraic properties and graph properties, and also something in the probability. This is just the motivation.
Thank you, Prof. Nabil. Semoga menjawab ya pertanyaannya.
Ya, terima kasih Pak. Terima kasih Prof.
Oh,
Sudah. terjemah.
Dr. Pugu, you want to ask also? Dipersilakan, Pak Pugu.
Thank you, Dr. Samsul Arifin. I just want to say about I agree with Professor Ahmad Erfanian about the student attention in the class is quite important to understand the abstract algebra. So Professor Ahmad Erfanian developed some beautiful concept of abstract algebra, but in the view of graph theory. So I try to can I show something? This one. I try to compute Jacobson graph of Z6 across Z6 with the sun and fractal tree, and surprisingly the result is so beautiful. So perhaps with this kind of feature, so the learning on algebra will be beautiful. Okay.
Just let me give you one comment for Fugu.
Yeah.
You know that we defined Jacobson graph for a ring, right? By Prof. Pucci. Now I defined some graphs related to Lie algebra. So it's interesting
Oh,
for
really?
you to know about Lie
Yeah.
algebras. Yeah.
Thank you for the information.
Right.
Okay, thank you about the comment and the apa from Dr. Pugu and Professor Ahmad Effanian. And we will move to the question in chat box from Carol Dupino Pereira. I will reading the question first. Excuse me, I have one question for for uh, Prof. Evanian.
Yes.
The term Keplot graph is used. Is this a stand graph theoretic term? If not, what is the most plausible intended term, and why is it a suitable candidate? And this is a true or false question. Every field is an integral domain. Thank you.
Okay. Let me ask first for the second question. So every field is an integral domain, but the converse is not true. But if the integral domain is finite, then it will be field. So every finite integral domain is field, but every field is an integral domain. An easy example for that a field is integral domain, so you can take real numbers. So real numbers is a field and is integral domain. And you can see that for integral domain, we have to prove that if the multiplication of two elements is 0, one of them must be 0. So if we take two elements, for example, A and B, so if A and B is 0, we have to prove that A is 0 or B is 0. If A is 0, so the proof is complete. But if A is not 0, because we have a field, so we have inverse. So if we multiply the inverse of A to AB, so we have A inverse AB is 0, and it means that B is 0. This is the proof for every field is an integral domain. But the converse is not true, because if you take the integer numbers, this is an integral domain, but it's not a field. If you take, for example, number 2, the inverse is half, but half is not is an integer. So this is answer for the second question. For the first question, we have many kinds of graphs. I just mentioned about simple graph. Simple graph means that simple and undirected graph. Simple graph, it means that we don't have any loop and any multiple edges. But if we consider a graph maybe is directed, or maybe we have more edges between two vertices. So we have different kinds of graph. Here, I just use simple graph. Simple graph is a graph with no loops and no multiple edges. This is the graph which I use. But there are many kinds of the graphs which we can. It depends on our algebraic concept. Sometimes we may use, for example, left zero divisor or right zero divisor. So we have to define a directed graph. Or sometimes we have left ideal or right ideal. So we need to use the direction for directed graph. So it depends on our algebraic concepts. We can choose which of the graphs are suitable here.
Thank you, Professor Ahmad Evanian for the answer. Yeah, Carol. Okay, thank you very much from Carol. Maybe the next question. Okay, maybe parallel with waiting for the other participant, I will ask again for Dr. Buku. This is about topics ya. How can I think the audience in this webinar is dominant with undergraduate student ya. How can undergraduate students can start exploring mathematical problem or mathematical research topics from classical problems, and how might the problem or this problem can connect to other fields, exclude from mathematics, such as maybe geometry or number theory or data science or computer science and the others. Thank you.
Okay, thank you for the question, Dr. Samsul Arifin. Perhaps in my opinions, there are some ways to determine the research topic. The first one, perhaps like a traditional method. So we implement like a literature review to see what the research outcome from the latest published paper. For the second one, some published paper already explain about the open problems. So we can try to seek the solution of that kind of open problems. But currently we have some attractive tool like systematic literature review method to see what the hundred or thousands papers says about some topics. So we can use that kind of tools to seek what will be investigate for further exploration, especially on algebra. By this method, we can also use like meta-analysis to see from thousands published paper related to specific topic, and also to see the contribution of that kind of paper, so we can see the impact about the paper. For example, the research paper on radical theory, we can see that what kind of paper that cite that paper with the meta-analysis. So we can conclude that there are three methods to see or to determine the topics. The first one is the traditional one. So we can see the research gap on the latest published paper. And the second one is systematic literature review. And the third one is meta-analysis method. I think that's all from me. Maybe from Pak Ipin or Professor Ervanian also have some opinion.
As you mentioned, so if anyone can start research, so first of all, they have to see that what's the topic and what's the background need for the research. So the background is very important. If you want to do something on algebra, so it means that you have to know more or enough things in algebra. So with poor background, it's difficult to have a research, right? So it means that first you have to improve your background on that topics, and then see the papers on that area which you are interested. And after just reading some papers, then you can see that what's the open problem, what's the conjecture, and you can start with them. So my suggestion is that first you have to read, you have to improve your background. So you have to just maybe attend in some classes to improve on that topic. If you want to do something on data sciences, so first you have to know some things about the just data science, and you have to pass some courses. So this is very important. And also, Dr. Pogo mentioned something about the field radical rings, right?
Okay, thank you for the answer, Dr. Teguh, and the comment, Professor Ahmad. And maybe this is the last question, yeah, in chat box for Professor Ervadian. I have from Unita. This is my elder sister, yeah, in Universitas Gadjah Mada in some years ago. I have two questions to Professor Ervanian. First, you mentioned some graphs with finite vertices. Are there examples in algebraic graph theory of graphs with infinitely many vertices? Secondly, I would like to start doing research in graph theory, but I often get stuck when trying to define the adjacency relation between two vertices in a meaningful way. You mentioned about like algebra graph also. It sounds interesting. Do you have any suggestions on how to begin research in like algebra graph?
Right. So the first question is that it depends on a graph. So when we define commuting graph, so in definition of commuting graph, we have not considered this definition for only finite groups. So if we have infinite groups, so we can have commuting graph. For example, if you take the group of integer numbers, so take Z, right? So we have many vertices, and of course we will have many edges, or maybe some other infinite groups. So depends on the definition. Sometimes we need to have finite group or finite rings for our definition, but sometimes it's not. So why we just assume that mostly the group or ring to be finite? Because in this case we can find the graph properties much easier than to the infinite. if the graph is infinite, sometimes it's difficult to find the properties. For example, if you want to check the connectivity, so for infinite graphs is a little bit difficult. So that's the reason that we mostly would like to assume that the graph is finite, but you can define for infinite graph. For the second question, just let me just mention about a graph related to Lie algebra. And I'm sure that Dr. Pogo is interested to see that what's the graph related to Lie algebra. So if you take a Lie algebra, for example, of dimension 2, 3, not just finite dimension Lie algebra, because in this case, as you know, Lie algebra is a vector space. So if we consider a finite basis and the field also is finite, right? So the number of elements in Lie algebra is finite. So if Lie algebra has dimension n and the field is fq, so the number of elements is q to the n, right? Now, in Lie algebra, we have the bracket x and y. Now, we can use this bracket to define a graph. So, for example, we can put all vertices as just elements of Lie algebra, or sometimes we may remove the central elements, right? And two elements, x and y, are adjacent if the bracket x and y is 0, or the bracket x and y is not 0, right? So this is a definition for the graph related to algebra. So the vertex set consists all elements of Lie algebra and two vertices x and y adjacent if the bracket x and y is 0. It's similar to the commuting graph. So we can also define the probability for the Lie algebra, just the set of pairs x and y, right, such that the bracket x and y is 0. Number of these pairs divided by size of Lie algebra squared, total number of pairs, and also some similar definition. I have some papers on just commutativity degree of Lie algebra and commuting and non-commuting graphs on Lie algebra. So maybe I can send to you okay, to know more about this sort of graphs related to Lie algebras.
Lie algebra. Thank you, Professor Ahmad Irfanian.
Okay. Thank you for the answer. Thank you, Prof. From Dr. Junita. Yeah, I think it's we'll finish this section ya. As we come to the end of this session, maybe allow me to summarize a few key points from Dr. Pugu and Professor Ahmad discussion this session. From Dr. Pugu, we maybe gained perspectives on mathematical education, algebraic modeling, and international collaboration. Emphasizing how theoretical concepts can inspire innovation and learning across topics. And from Professor Irfanian, we learn about the deep connection between group theory, graph theory, and maybe probability. Probability theory, particularly in understanding probabilistic and structural properties of some algebraic systems. Together, both talks reminded us that Mathematics is a universal language, capable of building bridge among scholars and nations. On behalf of the organizing committee, I would like to thanks to our speakers, Dr. Pugu and Professor Ahmad Ervanian, for sharing their valuable knowledge and time with us, and for all participants for your attention and enthusiasm. Let us close this session by once again expressing our gratitude, and may we continue to strengthen our academics ties and collaborative research in the field of mathematics and the other topics. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh. Mrs. Lia, the time is yours again. Thank you.
Okay, thank you, Dr. Samsul Arifin. Thank you, Dr. Pugu and Professor Ahmad Irfanian for excellent discussion. Now, on behalf of the organizing committee, we would like to symbolically present certificates of appreciation to our two speakers. Please, Dr. Samsul. Thank you once again for your valuable contribution to this international webinar. Okay, thank you, Dr. Samsul. Ladies and gentlemen, we have reached the end of today's international webinar of Algebra. We truly appreciate your participation, attention, and enthusiasm throughout the event. May today's discussion inspires further research and collaboration in the field of algebra and mathematical sciences. Thank you once again to our speakers, moderator, organizing team, and all participants. We look forward to seeing you again at our next academic event. Have a wonderful day, everyone. Thank you.
Thank you, Dr. Pugu, Profesor Ahmad Irfanian.
Okay.
Sehat-sehat semuanya untuk semua peserta.
Okay, thank you very much. I hope that
thank you.
to meet you not virtual, but in face in your university, inshallah, in the near future.
Okay. Okay, I will close this Zoom meeting. Keep healthy, everyone. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh.